Dean, SDO has been flying for over 2 years now. What are some of the things that we're learning from the imagery that we're getting from SDO?
Well, SDO doesn't just have images, although we are seeing very nice prominence eruptions that go up high above the sun and then crash back down, and that's been pretty nice to watch. And people tell me they've never really seen that before, so it's an opportunity to see something that we could have seen for a long time, but are only seeing it for the first time. It's nice to see things that we kind of know and thought we understood, and see them in ways we now know we don't understand. But we're also able to see sunspots before they show up. If we look at a chunk of the sun, watch this chunk of the sun go, and they see a sunspot, and then they rewind the data, and because we take the data all the time, if the sunspot's in the middle of the disk, they can always rewind it out to the edge and see if they see the signature of that sunspot before it breaks through the surface.
So are you suggesting that because of SDO at some point we'll know enough about the sun where we can see those indicators and maybe predict a sunspot days in advance of one actually happening?
We're hoping for hours right now. Oh. So it's not exactly an easy thing to see. The signatures are very faint, and they're working with data from SOHO, and now they're working with data from HMI to try and move it back further and further. It would be nice to be able to see them all the time, but we only get to see the sun about half of a rotation. It takes about 28 days to go around. We only see it for about 14 days. So if we can see a sunspot several days in advance, that's about the best we're going to do with our satellite.
Well, now you mentioned something very interesting. You said obviously we're getting imagery, but that's not all we're getting. What are the other kinds of data that we're getting as a result of SDO?
We have an instrument called EVE that looks at the sun as a star. And it looks very out in these EUV wavelengths. You see a lot of these pretty images, or in what we call the extreme ultraviolet. EVE measures the brightness of the sun in the extreme ultraviolet and in many different wavelengths. And EVE, when it first turned on, started seeing flares. We'd never really seen flares in the EUV before. We had seen them in X-ray. We see them all the time in X-ray. We see them in the visible, but we had never seen them in the EUV. And when one of our students started looking at that, she realized that the amount of energy in these extreme ultraviolet was more than the energy we saw in X-rays. So from a space weather point of view, you're looking at changing the atmosphere of the Earth in different ways. And so this is a very important result from EVE, is that we see flares differently than we ever have before.
Now when we get to space weather predictions in the future, are we going to see a magnetosference alert or an EVE alert or anything like that? Is that the kind of thing that we'll see?
We already do some of that inside.
Okay.
We haven't quite developed a magnetospheric index, but we're working on it.
Yeah, well, I think that's a very good idea.
You would like that, right?
Yeah, I would very much like that. I'm begging you, I'm imploring you, please work on that. That would be fantastic.
We do have EVE flare watches and stuff where they are trying to say whether or not a flare will happen in the next 24 hours. And they want to turn their instrument on a certain mode if they think that's going to be true. So they are working on predicting for the next 24 to 48 hours. We are working on doing all different kinds of prediction. When you look at the AIA images and you see a lot of loops, you want to know, is there a flare going to happen? And people just want to know, if I can look at the loops, can I see a flare about to happen?
Well, another big thing that we're clearly talking about now is the Venus transit. And one of the things I wonder, from an SDO standpoint, what do you expect to see during the transit from SDO's perspective?
We know exactly where Venus is, and we can calculate where it's going to hit the edge of the sun. And we can translate that to what the roll angle of our spacecraft is. Because our spacecraft is out there in space. And it's pointed more or less to the north and south pole of the sun. And we think we've got it pretty good. But it's nice to have a little independent check. And that's what Venus is going to give to us. It's going to go on a certain angle of the sun. It's just a clock. It's just like it goes on the face of a clock. And we're going to look up what the spacecraft says that angle is, and we're going to be able to adjust our pointing just a little bit.
One of the things that we were wondering about is what would you expect from SDO's perspective if during the transit we saw some significant solar activity, either a flare or a CME during the transit? What would that look like from SDO?
Well, if Venus wasn't there, I mean, Venus takes 6 hours to go across the sun. During that time, a flare will probably happen. So there'll probably be sunspots, there'll be flares happening on other parts of the sun. But it'd be kind of cool to see one that happened as it went across. What we can do then is EVE can measure the total amount of radiation coming from the sun, and then Venus would block it, and we would measure the change in radiation, and that would tell us how much energy was coming out of that flare. Because, so it's actually, that would really be cool if Venus covered up a flare as it went across, because that's how we measure the total energy that comes out of a flare.
Okay, so that's great, because not only would that be something aesthetically amazing to see happen, but you actually could gather some significant scientific data should that happen.
That's correct. We'd love to see that happen. Can you arrange that?
Yeah, I'll see what I can do.
You have friends that...
well, you know, I have been known to have absolutely zero influence, so we'll see how far that goes.